So yet another approach to calculate or approximate the posterior is what is called a variational base. Actually, now we are going back to these notations where we use y for the data. And so again, we want to calculate this p of theta given y, the posterior, and it comes from the base rule. And the idea in the variational base is to again approximate the posterior distribution with a probability distribution called q of theta. So we approximate our posterior theta given y with q of theta. And this q of theta, the requirements for this q of theta is it's easy to integrate it and it's easy to sample from it, and we'll see why. And the way we're going to calculate this approximation is we're going to pick a family of distributions let's say, simplest possible family is p of theta is just the product of phi theta I given mu I and sigma I squared. It goes from 1 to p, so we have p parameters theta, and this one is just normal density. Okay, so we say, okay, we don't really know what the true posterior is, but we're going to approximate it as a product of univariate normals. And so now the parameters of this approximation are those mu's and sigmas, and we're going to call those parameters phi. And so let's say we want to approximate posterior using product of univariate normals, and this product of univariate normals is parameterized by phi, and we need to find the best possible value of phi. And the way we're going to do it is by looking at what's called Kullback-Leibler divergence. It's just the way of measuring the difference in two distributions, and we're going to calculate KL divergence between distribution Q and distribution P of theta given y, our posterior, and we're going to find Q that minimizes this KL divergence. So we're going to call it Q star, and Q star is the distribution that minimizes KL divergence between Q and P, and the scale divergence is given by this integral, so it's Q times the ratio the log of the ratio of Q and the posterior that we're trying to approximate. And again, so this is just in a minimization problem. If you have some parameter phi that parameterizes this distribution Q, then essentially you want to find the minima with respect to this parameter set phi. So we converted problem of integration to the problem of optimization. And let's look at how to calculate this KL divergence. So there are a couple of things that we need to keep in mind. We're actually going to skip the algebraic derivations, but what we can show that the minimization of the KL divergence between Q and the posterior is equivalent to minimizing what is called a lower bound. Lower bound is just the expectation, an expectation of the log, and on the log we have prior times the likelihood divided by Q, and we know how to calculate this, and this, so we have everything that we need to calculate this ratio. And essentially now we have an optimization problem. Optimization problem only involves things that we know how to calculate. So we're going to call this function h of theta, and essentially we want to calculate expectation of this function h of theta. Now the question is, how do we minimize this expectation? First of all, it's an expectation, and it's expectation taken with respect to this distribution Q. And we're going to use gradient descent, same thing we did before. So the two things to solve this problem. So first thing, we're going to use Monte Carlo approximation we're gonna approximate this expectation with a Monte Carlo approximation. So we're gonna sample from this distribution Q. We're gonna sample a whole bunch of parameters theta, and we're gonna calculate expectation using that. And the second, we're gonna use stochastic gradient descent to calculate the next iterate in this optimization loop. Now we know how to calculate Markov chain approximation. The question is, how do we calculate stochastic gradient descent? In stochastic gradient descent, we have to calculate the gradient of the expectation, and that's not that trivial of a task. The problem is that gradient of expectation is not equal to expectation of the gradient. So we cannot just simply take the gradient inside the expectation and calculate the gradient of the h of theta. So there are a couple of ways to calculate the gradient of the expectation. Is one what is called as a reparameterization trick. Again, we're not going to talk about the details of it. You can learn about it more if you want on your own. But we are able to do that. In the context of a rational inference, it's doable. So we can rearrange the term on the expectation. So essentially, we're going to get another expectation at the end, and so we can implement stochastic gradient descent to calculate the parameters. And the last item we're going to talk about is this Langevin stochastic gradient descent or Langevin dynamic. And this is probably the simplest way to do the Bayesian inference. And the idea is based on this Brownian motion idea. Brownian motion idea is that so you have a typical, so you have your second Newton's law that says that mass times acceleration equals to force. And if you think of a force of a particle, and we're going to look at the case where you actually have friction. So in this case, the force equals to some minus gamma times the velocity. And so that's the friction force. Plus some other forces that affect the particle. Plus, we're going to add this, we're going to call it epsilon, which is some random force. And that was the observation that was made by the Brownian, by Brown, who was the biologist. He observed that movements of the pollen particles. And he saw that they look like they're randomly moving in different directions. And of course, the movement are not completely random. They just get affected by the forces. But we don't really know how to study those forces in the micro level. So in order for us to study them, we just assume the forces are random. And then once we assume that, the second Newton's law actually works. And that's the whole motivation behind stochastic dynamics. And also we're going to look at the case where we have overdamped system, means that the mass is very low and acceleration is very low. So we essentially can ignore this term mass times acceleration, and we have this second Newton's law. So it's friction term plus the random force plus all the other forces that affect the particle. And so we're gonna rewrite the force as the gradient of the energy. And if we do that, we can just calculate the dynamics of this Brownian system. Essentially, it's a Brownian Brownian motion, discrete version of the Brownian motion. At the next iterate, we take the current iterate and we apply this random force and the other force, which we call which we write as a gradient of the energy. And since we discretize things, we have to introduce this time step here. And we introduce this gamma. We divide both by the gamma to make things easier in the future. And essentially that's what we do. If you look at this equation, it's actually very similar to your gradient descent. You remember in your gradient descent, your next iterate is your current iterate plus some learning rate times the gradient of the loss function. And in the Langevin dynamics, we replace it by the next gradient equals to current gradient plus some random number plus the step in the gradient direction. Actually, sorry, we have to have a minus here. So this one and this one has to be minus plus epsilon minus alpha. So that's it. That's all we do. At every time of the gradient descent, we just add a random noise to the parameter theta. And you can think of it, so you have your theta, your current theta, and the gradient descent puts it to a new position, and then you say, okay, from this position, I'm just going to have this random move. And you randomly generate noise, and you add noise, and you relocate your gradient rate, and then you start from here, and you keep doing like that. And you can do this process many times. So every time you have this trajectory of the parameters theta. And what you can show that is that the elements of these trajectories are actually samples from your posterior distribution.